We also will simplify by canceling any substances that appear in both the reactants and the products for the different reactions. So let's do an example. This figure also comes from your book, just sort of a visual way of doing the balancing. Start with other atoms, balance oxygen, balance hydrogen, balance electrons. Okay, so basically this question is asking you to balance the equation and then figure out the coefficient in front of the hydrogen ion once it's balanced. This is a great multiple choice type question, okay? So we'll go through our steps based on the last slide. I'm just gonna go ahead and do that. Is everyone okay with that? So we're gonna balance first, then we'll answer the question. So the first thing to do is write the half reactions. When you write the half reactions, pick out the atoms other than oxygen and hydrogen that are in the equation and write them on either side of the arrow. Keep them together, similar ones together. So MnO4 minus, we're going to put that on our reactant side, and we're going to go form Mn2 plus. We're going to leave the bromine. That's going to be a separate half reaction. So we'll have bromide on one side. Guess I should write my phases in. And that's going to form liquid bromine. Okay. So there's our half reactions. Again, I took the two species that weren't oxygen or hydrogen, found them on the reactant side, product side, made them into a half reaction, did that with what's left over. So manganese one, bromine one. Okay, so now we balance our other atoms, so things other than oxygen and hydrogen. We've got one manganese on the reactant side, one on the product side in our first half reaction, so that one's good. For bromine, we have one bromine on the reactant side, two on the product side, so we need to balance with two bromide ions. Now we'll take a look at the oxygen. I wonder if I can move these. No, okay. Anyway, for our first half reaction with the manganese, we have 4 oxygen on the reactant side, none on the product side. So we need, in order to balance out the oxygen, we need to add 4 water. Okay, everyone see that? On the second half reaction, we don't have to worry about oxygen. Now that on the first half reaction, now that we've added the water, we have excess hydrogen on the product side. So we need to add hydrogen ion on the reactant side in order to balance that out. So we have a total of 8 hydrogen on products, so we need to add 8H plus on the reactant side. Okay, we're good on the second half reaction. Questions so far? Okay. Now we're going to balance the electrons. And notice that we haven't figured out the oxidation states for anything. You actually don't need to in order to balance the electrons. And it's actually much easier if you don't even think about it. I don't know if I should tell you that, but that is true. I find it easier for myself. So what I'm going to do is total up, or sum up the charges on the reactant side and the product side. So we have 8H plus on the reactant side and 1 minus charge on the reactant side. So we have a total of plus 7. And on the product side, we have a total of plus 2. Everyone see that? So if we want to make the charges equal, and we can only add minus charges, okay, for our electrons, What do we need to add into which side in order to balance out our electrons? How many? 5 electrons. Which side? On the reactant side. So now our total, if we include our electrons on the reactant side, is +2. That make sense? On the second half reaction, we have 2 minus charge on the reactant side, a total of 0 charge on the product side, so we can add 2 electrons on the product side. Now we have 2 on the reactants, 2 minus charge reactants, 2 minus charge on the products. Yes?
Why would the hydrogens be could it be 4 H2
It's got to be H+, because we're asking you to do it in acid. Yep. Yeah, so adding H+ is key. Other questions? Okay. So now the next thing to do is sum up our equations, but we need to be able to cancel out the electrons. So we've got 5 electrons on the first half reaction, 2 in the second half reaction. We need to multiply these so that we can cancel out all electrons. So I'm going to multiply the first half reaction by 2 and the second half reaction by 5 in order to be able to get 10 electrons for each half reaction and be able to cancel them out. And I'm just going to rewrite everything down here with the multiplication. So we're going to have 10 electrons plus 16H plus 2 MnO4 minus, forming 2 Mn2 plus 8 H2O. I've left all my phases off, please excuse me. And for the bromine half reaction, we're going to have 10 bromide ion forming 5 bromine and 10 electrons. Everyone okay with that? Okay, so if we sum up these equations, we're going to cancel out the 10 electrons, because they're showing up in the reactant side of the first reaction and the product side of the second reaction. And those are the only things we can cancel. So we're going to end up with 16H plus 2 MnO4 minus aqueous plus 10 Br minus aqueous, forming 2 Mn2 plus aqueous plus 5 Br minus aqueous, 5 Br2 and that's a liquid. And that's it. No, 8 H2O. Okay. Did I get everything? 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. Questions on that part? Does this feel familiar? Okay. So if we go back to our question, the question is, what's the coefficient for H plus and which side is it on? We've got 16 proton and it's on the reactant side, so our answer is E. Yes?
Should you, since they're all divisible by 2?
But if it was, yes. If it was divisible by a whole number, then you could reduce everything. Common denominator. Lowest whole number coefficient is what the question uses. All right, do you want to do another example or should I move on? Do another one. Okay. I think I might have you guys work on it and I'll walk around. Okay, same sort of question, still looking for the whole number for H+. Now you've got a different reaction. That's really the only difference. All right, for the sake of time, I'm going to keep moving. I will, for this problem, write up the half reactions that I end up with before I cancel everything out and add them together. So I'll end up with 6 electrons plus 3 S2O8 2 minus, forming 2 SO4 2 minus. Then I'm going to have 2 water plus NO forms NO3 minus plus 4H plus 3 electrons. And I messed that up because I need to multiply all of that by 2. Okay, well, in parentheses times 2. And you should end up with 8 hydrogen ion on the product side. So what I'll do, I have a worksheet that goes through a whole bunch more of these. I'm also willing to make a couple videos if you'd like to see some more. I know that, at least when I've taught this course in the past, this is something that should be easy, but is not at all. Like, it's like you follow the pattern, you can eventually get it, but you really need some practice. So I definitely recommend practicing the balancing. Okay, yes? And which one? Yeah, so I've, did I screw something up?
Yeah, that's 208 1.
Oh no, I forgot. No, you know what I did is I looked at 2 different lines on my notes here. This should be a 6. Yeah. Sorry about that. Okay. Again, yeah, this is a great place to make quick, easy mistakes. We're on this. All right, let's just move on a little bit here and talk about balancing in base. So balancing redox reactions in base, you do this, you start the same way as you do for acid. So you basically do steps 1 through 4 in the previous slide. Then what we're going to do is look at the number of hydrogen ion that we have, and we're going to add hydroxide ion, the same number of hydroxide ion to both sides of the equation. And what we're going to do then is combine H plus and OH minus to form water, because we know that when we add strong acid to strong base, it completely reacts to form water. And then we're going to simplify our equations and cancel substances that appear in both the previous slide says we're going to note the number of H plus and add this number of hydroxide. Last step says to combine H plus and OH minus where they exist on the same side of the arrow, and reactants and products. Okay, so do an example here with iron hydroxide and water, and hydrogen gas. So I'll walk you through this one again, starting with the way we've done it with acid. We're going to write our half reactions. So the first one, we will have FeOH2 forming iron, and that's a solid. Not that it really makes that much of a difference in the balancing. Plus water. Nope, not yet. Okay, that's our first half reaction. Our second half reaction, then we're going to have the H2 forming H2O. Okay. Now we're going to balance for atoms other than oxygen and hydrogen. So for the first half reaction, the only option there is hydrogen, and it's balanced. In the second half reaction, there aren't any, so we'll ignore that for now. Then we balance for oxygen. We've got 2 oxygen on the reactant side in our first half reaction. So we're going to add 2 water to the product side. I'm going to keep working with this first half reaction. Because we've added 2 water to the product side, we now need to add 4 hydrogen ion to the reactant side. Did I do something wrong? Yes. Oh my God, you guys. 2, because there's hydrogen in the iron hydroxide. I know when there's whispering that I'm making a mistake. I like that. But you could also just tell me. Okay. In the second half reaction, we have H2 on the reactant side, H2 on the product side. We need to add 1 water to the reactant side to balance. And now we have 4 hydrogen on the reactant side, 2 on the product side. And we get 2 H plus on our product side. So if we were to now add in the electrons and sum everything up, we would have balanced in acid, but we want to balance in base. So as our to both sides of the equation. So we have 2 H plus in the reactants for the iron hydroxide half reaction. So we're going to add 2 OH minus to the reactant side. I'm going to fit that in here. And we need to add that to the reactant side and to the product side. Because you can't just add something in this case without making it equal. All right? It's like adding a whole number coefficient to an equation that has like variables on both sides of the equation, the equal sign. You have to add to both sides. So in the second half reaction, we have 2 H plus. We need to add 2 hydroxide to both sides. Everyone okay this up to here? Okay, now water, and then we can cancel things out. So in our first half reaction, we have 2H plus and 2OH minus. Those are going to combine to form 2 water. And I'm going to rewrite my equation now. 2H2O plus iron hydroxide. It's going to form iron solid plus 2 water plus 2OH minus. For the second half reaction, we have 2H plus and 2OH minus on the product side, so that's going to combine to form 2H2O. But on the reactant side, we're going to have 1 water plus H2 plus 2OH minus, forming H2O plus 2H2O. It's kind of a fun one. What's up? Yeah, you could say 3H2O. All right, we need to do our electrons. And I probably should have done my electrons before we did the adding hydroxide, but it'll work out both ways. So in the first half reaction, we have 2 negative charges on the product side, so we need to add 2 electrons to the reactant side. And in our second half reaction, we have 2 minus on the reactant side, so we can add 2 on the product side. Okay. Conveniently, we don't need to multiply anything in order to cancel out our electrons. So let's start canceling things out. We'll start with those electrons. Those are going to go away. We're going to have the 2 water and the 2 water. We're going to have 2 hydroxide, 2 hydroxide. And we're going to have this water and 1 of these. So we'll end up with iron hydroxide plus H2, whoops, have it, forming the iron plus 1 water, 2 H2O. All right, questions on that? So our answer here is we end up with 0 OH minus, which is fine. I mean, we've balanced in base, we've gone through the whole thing. It's kind of an unusual one to end up with 0 hydroxide when you balance in base, but it's kind of a fun one too. All right, questions on anything? Okay. So then let's begin our discussion on voltaic or galvanic cells. These terms are used interchangeably. So this is where we're going to take chemical energy and turn it into something useful. So a voltaic cell is a device that's going to generate an electric current. And basically what we're going to do is take a spontaneous redox reaction, and we're going to generate electricity. And so this is an example of a really rudimentary electrochemical cell. We have half reactions. They occur in these beakers separately, sort of, but they are connected electrically through a voltmeter. And then there's also some salt bridges, which we'll talk about in a little more detail. One of the classic examples that you'll see for a galvanic cell is that where we are oxidizing zinc and reducing copper. And these are the half reactions. You can combine these to get an overall zinc solid plus copper 2 plus. It's going to form zinc 2 plus copper solid. Okay. These half reactions that we write, and those that we've written, in our balancing chemical reactions, those are what's taking place in these beakers. Okay, they are separated, at least for the most part, by the beaker, but they are connected electrically by wiring. Okay, so here's another look at our zinc copper galvanic cell. It's kind of interesting how these work, and so let's look at the zinc side. So we have oxidation taking place. We know that because we're forming two electrons. Oxidation is loss of electrons, so the electrons show up on the product side. So that's a good sign that you have an oxidation. And we've got a solid zinc rod that's in a solution that contains zinc ions. So this could be like a zinc nitrate solution or something like that. And what's going to happen is we're going to connect our zinc half reaction to our copper with a salt bridge. That's one of the things. This salt bridge is going to allow for ions to migrate. If we didn't have a salt bridge there, some electrons would flow from the anode to the cathode. We're going to get to these terms too, but eventually it would stop. It would stop relatively quickly in the process, and that's because we need to essentially balance charge. You can't have a beaker that only contains minus charges and another beaker that only contains positive charges. So this salt bridge allows for positive and minus charges to flow in the proper directions to allow the reaction to actually take place. Did you guys make a galvanic cell in lab yet? Probably will, if you didn't. Was that? Next week. Your salt bridge is likely, it could just be a piece of filter paper that you drape across the beakers, but it could also be something more complicated. I'm not sure what you guys are going to use. Okay, so on for the other half reaction, we have a reduction taking place. We're gaining electrons, reduction is gain. The electrons show up on the reactant side of the half reaction. And again, in terms of our solid, copper is a piece of copper wiring or sheet in the solution of copper ions. And so the way that the electrons are going to travel, this is important, electrons will travel from the anode to the cathode. And the anode is the place where oxidation takes place. That's the definition. And the cathode is where reduction takes place. Okay. There's another saying for remembering oxidation occurs at the anode. So it's the one that I like is an-ox. Remembering that reduction occurs at the cathode. You can have red cat. You can also remember that anode and oxidation both start with vowels. Reduction and cathode start with consonants. Okay. Okay, so our electrons go away from the anode to the cathode. In our salt bridge, we're going to see that the cations are going to migrate towards the cathode, okay, to balance out the negative charge. And then on the anode side, anions are going to migrate towards the anode. The other thing that's kind of neat, so there is actual chemistry taking place on the surface of these metals. That is the actual process that we're drawing here. So a solid zinc atom will lose electrons and enter into solution. And then on the reduction side, copper ion will form and bind isn't the right term, but will adhere to the copper solid. So if you were to let this galvanic cell run for a really long time, you would end up with a much larger piece of copper and a much smaller piece of zinc. Okay, that's kind of neat. All right. So for instance, one sodium wouldn't like migrate all the way. It's going to interact with other ions, and they're all going to move sort of in tandem. A reactant or a product. Okay, oxidation, you're going to have products, electrons as products. Reduction, you'll have electrons as reactants. Are traveling from the anode to the cathode hydrogen electrode and put it in one of the halves in the half reaction. Okay, so anode, I think we did these already. Anode's where the oxidation occurs. Cathode is where reduction occurs. And then, of course, the salt bridge allows for electrons to flow. Electrons do not flow through the salt bridge, though. Okay, it's the counter ions that are flowing through the salt bridge, and they're not really going through. Like you wouldn't take one anion. Anyway, are okay. So do I want to have you do this? I'm going to leave this to you guys. So this is another redox reaction that does occur spontaneously, so it works in a galvanic cell. When you write this you can write this as half reactions, and that's going to be one of your tasks. So write the half reactions, and then remember that oxidation occurs at the anode, and reduction occurs at the cathode. And given that, you can figure out where each half reaction will be. Will it be at the anode or the cathode? And again, that's judging based on whether the electron, okay, then I'll let you do that one. Okay, there's a couple other terms that we're going to need to be able to understand what's happening in a galvanic cell. One of them is Electro-Motive Force, which I probably won't use very much, but it's also known as the cell potential. Okay, and it's essentially a potential energy difference between the two electrodes in a galvanic cell. Okay, we measure the potential in volts or voltage. And 1 volt is going to be equal to 1 joule per coulomb. Coulomb is related to the charge in the current. We'll go into that in a little bit more detail. So you can think about a galvanic cell and a potential as sort of like potential energy related to things you're much more familiar with, dropping a ball from a high place, or water going down over a cliff, waterfall. So here we have high potential energy, and now we have low potential energy. And because our electrons, we'll see that we have a high potential energy at our anode and lower potential energy at our cathode. And that's just like saying that the water flows from the top of the waterfall to the bottom, not the other way around. Okay. Other half reaction would occur in the other cell. Main thing from that is we're going to measure potential in volts. Right? There's a lot of convention that goes into reporting cell potentials. we are going to use what's referred to as the standard reduction potentials for a half reaction. And we're going to look at the two half reactions and essentially sum them up to figure out the cell potential. The way we measure reduction potentials is against sort of a baseline. And that baseline, a reference value, is the reduction of H plus to H2. And that's in what's called the standard hydrogen electrode. So the value, you're going to be able to look up standard reduction potentials. They're in your book, table 20.1. All of those values are listed relative to a standard hydrogen electrode. A standard hydrogen electrode is just an electrode that was devised. It's actually kind of dangerous to use because it involves hydrogen gas, and it's acidic. So these tabulated values are sort of, people don't really measure them anymore. But anyway, it's just relative to what is measured against a standard hydrogen electrode. Basically, and we would figure out the potential from a voltmeter. What's my point? I don't know. But we just assign that value as 0. Okay, that's the one thing that's important. So everything is relative to that. I sort of mentioned this, but in order for voltaic or galvanic cell to work, we must have a positive value for the E cell. And we're going to see that our cell potential is related to our Gibbs free energy. And if the cell potential is positive, we end up with a negative value of delta G, which means it's spontaneous. Okay, so that's, we'll come back to that. But this equation, the cell potential, you need to be familiar with. So what we're looking at is the actual standard reduction potential for the half reaction that occurs at the cathode, and the standard reduction potential for the reaction that occurs at the anode. Now, these are both reduction potentials, even though oxidation is occurring at the anode. Okay? So you'll still go to the reduction potential table and you'll still look up that value. And the reason why that works is because there's a negative sign. Okay, so use this equation, put in reduction potentials. You don't need to reverse anything. Okay, no negative signs. It'll work. So if you were to look at table 20.1 and find the reduction potential for the zinc half reaction, this half reaction, zinc solid forming the 2+ ion and losing 2 electrons, you would find that the reduction potential is, where's my note? Minus 0.76 volts. And then on this half reaction, this is our hydrogen forming H2 gas. Okay, this is the value that we have assigned to be 0 volts. Okay, that's our standard, that's our baseline. So if we calculate the cell potential using the equation from the previous slide that I've rewritten here, okay, reduction occurs at the cathode. Reduction is gain. So there must be this hydrogen reaction where our reduction is. So we'll use 0 volts here for our reduction potential at the cathode, minus the reduction potential at the anode, negative 0.76 volts. And so our cell potential is 0.76 volts. And when you take a voltmeter and measure, that's what you're measuring. You're measuring the cell potential, and that's what this is trying to show you here. Okay? Just real quick, the next slide does the same thing. You can look at your table 20.1 in your textbook and look up this reduction potentials and actually calculate the potential. Make sure you get 1.10.